Welcome to In Depth with Academia. I'm Richard Price, CEO of academia.edu, and your host for today's deep dive into some fascinating research. You know, I love getting into the real nuts and bolts of academic work, asking, why does this matter? So today we're exploring a paper by David Lush, which has a pretty intimidating title, On the Bohr radius relationship to spin-orbit interaction, spin magnitude, and Thomas precession. But don't worry, we're going to break it down together step by step. Let me start by saying, and I like to emphasize this every episode, my goal is to present this work as neutrally as possible. I'm not here to say this is the final truth and nothing else matters. What we're doing is peering into someone's painstaking effort to uncover new insights and, sometimes poke at old ideas in physics, especially in atomic theory. So, what's the core question here? Why do people care about the Bohr radius spin-orbit interaction and this thing called Thomas precession? Let's step back for just a second. The Bohr radius is this holy grail number in atomic physics. It's the typical distance between the proton and electron in a hydrogen atom according to the Bohr model. It helps explain why atoms are the size they are. But most explanations rely heavily on quantum mechanics, a field that, honestly, can sometimes feel like wizardry with weird rules. But David Lush's paper says, wait a minute, let's try something different. He's wondering, can we find a more classical, almost old-school explanation for why the Bohr radius is what it is and how it links with things like the electron spin and these curious ideas about angular momentum? Now, why is this significant for you, the listener? Well, if you've ever found quantum physics baffling or kind of magical, this paper might appeal to you because it asks, is there a more intuitive, less mystical way to see these atomic behaviors? Can classical physics with some clever updates give us some understanding without the enigmatic leaps? All right, let's look at what the paper actually does. Lush uses a model that's a blend. It's got a classical flavor, but adds in some new elements. He imagines a hydrogen atom with an electron spinning in a circle around a proton, just like in the old Rutherford model, which, by the way, totally ignores quantum rules. But here's the twist. He gives the electron an intrinsic spin and a magnetic moment. That's a big deal because electron spin literally changed physics a century ago. This approach lets him analyze not just how the electron moves, but how its own spin and the angular momentum of its orbit interact, with something called Thomas precession thrown in. If you've never heard of that, honestly, you're not alone. It's a sort of precessing or wobble of angular momentum that shows up when things move fast, kind of like spinning a top on a moving train, and it starts to do something even stranger. Now, here comes the insight. Lush finds that the total angular momentum, that's the sum of the spin and the orbital motion, doesn't just stay constant like you might expect. Instead, it wobbles and precesses. But there's one, and only one, special case where it doesn't. When the spin and the orbital angular momentum are exactly opposite, they're anti-parallel, and the frequencies of their respective precessions, so how fast they're spinning around, are equal. Get this, when those conditions are met, the radius of the orbit you find is exactly the Bohr radius used in quantum physics. It's like the classical world and the quantum world are, for just a fleeting second, shaking hands. Lush also points out that earlier physicists, like Thomas himself, missed this because they didn't account for hidden momentum, which honestly is kind of a weird thing where a magnetic object in an electric field holds more momentum than you'd think. That's a rabbit hole for another day, but I once spent a whole weekend reading about hidden momentum and only ended up more confused. So, looping back, what's the takeaway for you? 1. This paper is a reminder. No theory ever gets the last word. Science is a conversation, not a monologue. 2. Sometimes classical physics, when cleverly updated, gives us fresh lenses on old mysteries. If you're the kind of person who likes to see how the sausage is made in science, this is a great example of how researchers question and reinterpret foundational ideas. Again, I'm presenting Lush's work neutrally. It doesn't mean I endorse his findings, but I think the value is in asking these questions and considering how our assumptions can be challenged. All right, I hope you enjoyed this episode of In Depth with Academia. I'm Richard Price, reminding you, research papers are invitations to curiosity, not declarations of finality. Thanks for joining me, and if you ever spin a top on a moving train, let me know what happens. See you next time.